Okay, hello. My name is Sophia Abrego, and I've been working with Professor Matthias Fitzpatrick for about a year now, and he's been a great mentor to me and has inspired me to really love research. And I hope to go to grad school and continue working on research like this. And Professor Matthias Fitzpatrick has been a great leader in encouraging me, and it's been awesome work. It's super exciting, and I really get to get my hands dirty and make like visual, tangible things. Working on studying TLS defects in superconducting qubits. So in classical computing, we have classical bits, 0 and a 1. But in quantum computing, we have quantum bits or qubits, which are a superposition of 0 and 1. So for example, if you were to have 3 bits, that would be 2 to the power of 3 combinations, which is 8 combinations. But the difference between classical and quantum computing is a quantum computer can process those 8 combinations at the same time, whereas a classical computer can only process one at a time. Because of this, quantum computers are being studied at a lot of institutions, and we want to study these qubits as well. So we are specifically studying Josephson qubits, which are great for TLS defect studies because they're nonlinear and have 2 energy levels which are isolated. This allows us to study these defects being pretty much the biggest villain to our qubits. They are found in dielectric materials and found on surfaces and oxide levels, and you can think of them as thieves that kind of steal energy from our qubits and lower the decoherence times of qubits, basically meaning that they reduce the memory of our qubits, which makes it very difficult for a quantum computer or a qubit to process information at the rates it can, its efficient rates that it has the potential to. So in order to study these TLS defects, we didn't want to take a conventional approach, which typically involves using resonators or qubits, which take a lot of complex fabrication and time and are very invasive in the way that they're manufactured. And also, you're only able to probe and look at small volumes of materials. So we designed a rectangular and square aluminum waveguide, which has a broadband, or should have a broadband drive of around 3 to 6 gigahertz. It's also a modular, non-invasive approach, and with our new design, it allows for polarization control with these orthogonal ports that we made.